Okay, so we're going to jump back into talking about membrane transport. Good job to most of you on completing the quiz by right now. I realized that apparently that didn't become live until Sunday. So the last few of you who have not completed it, I'll reopen it just until the end of today. So do get that done right afterwards. My apologies about that. But hopefully that gave you some good practice practicing this electrochemical driving force stuff. All right. So jumping back in, we're now going to be talking about transport. And when we're thinking about the direction of transport, we're keeping in mind all these things we've been talking about: the chemical driving force, the electrical driving force, and that combined electrochemical driving force. So when we're thinking about something that's not charged, we can just think about its gradient, chemical gradient. When we're thinking about an ion, we have to think about both the chemical driving force, the electrical driving force, and add them up together to get our electrochemical driving force. However, our rules about passive versus active are the same as they've always been. We're just thinking about whether we're moving in a favorable direction. In that case, it's passive transport. So we're moving with the driving force, or active, we're going to require energy because we're moving against the driving force being that kind of push of either the chemical gradient or the electrochemical driving force as a whole. So passive transport is going to be spontaneous. We're not going to require energy. We're often going to refer to this as downhill movement down a gradient. Now we have three types of passive transport. So we're going to have simple diffusion. In that case, we're just going directly across the membrane. So we're thinking about things that can dissolve across the membrane. We're going to have facilitated diffusion, in which case we're going to need a little help. And then we're going to have a special type called diffusion through channels, which is kind of going to go along with that facilitated diffusion. Okay. So for simple diffusion, we don't need any membrane proteins. It means that we are only going to be able to have simple diffusion when it's something that can move past those phospholipids, something that can move through that lipid barrier. Now, there are a couple of factors that are going to affect how fast that happens. So there are going to be factors that affect the rate. So the first is going to be the magnitude of the driving force. So like how strong a push we have. Also the membrane surface area. So when something diffuses across a membrane, essentially what's happening is all these particles are moving around, right? And they have to hit the membrane in order to go through. Right, so when we have more surface area, more membrane surface area, we're going to have faster diffusion across that membrane. And then membrane permeability. Just because something can get across doesn't mean it has the same ease of getting across as something else. So some things are going to take a little longer to get across just because of the properties of the membrane. Okay. So when we talk about rate of diffusion, so often we're going to refer to it technically as net flux. So net, just like we had net ATP, so like on the whole, flux is like movement change. Okay. So pretty simple relationship between net flux, so movement across the membrane, and the concentration gradient in simple diffusion. So as we have a greater concentration gradient, so it's greater difference in the concentration between outside and inside, we're going to see a faster rate of diffusion. We're going to see greater net flux. Now for simple diffusion, we only have to pay attention to the concentration gradient here, because anything that's charged, anything that would have an electrochemical driving force, it's not going to be able to diffuse across that membrane, because charged particles can't get through that lipid bilayer. So here we see an example of membrane surface area. So when we have a greater surface area, we're going to have faster diffusion because we are going to have more likelihood of basically running into a membrane to get across. So you can imagine looking at these two types of tissue, right? In this one where we have more surface area, right? We're more likely to sort of bump into one of these membranes and dissolve across. For these, we might bump into a membrane, but there's going to be a lot of time when we're kind of searching around for a membrane to hit it and move across, transported. So when we say that membrane permeability affects the rate of transport, basically different things are going to have different solubility in lipids. So first, in order for something to fuse across, it has to be lipid soluble because those phospholipids are forming the barrier. But some things, depending on their size and their shape, may have an easier time anyway. They may be more soluble in lipids than others. Now, if we were thinking about just in general, membranes and permeability, temperature would make a difference because temperature kind of affects the speed of particles as well as the fluidity of the membrane. But in human physiology, that's one of our regulated variables, our homeostatically regulated variables is temperature. So this shouldn't really be a factor in a human. The other thing is the thickness of a membrane. So if we have a thicker membrane, usually we're not going to talk about that when we talk about individual cells, but we might when we're talking about like cell layers. If we have a thicker membrane, we have like a layer of something else collecting on the side of the membrane, that's going to slow down our rate of diffusion, basically because we have to get through more stuff. So with low permeability and high permeability, greater concentration gradient, greater net flux. But if we have high permeability, that means whatever we're talking about has an easier time getting across the membrane. So we'll see that comparing something with high permeability to low permeability, the thing with high permeability or the membrane has high permeability too, is going to get through faster, more of it's going to get through simple diffusion. These are some things to think about as you are studying. And we're going to move through and think about carriers and channels. So when we're thinking still about passive transport, the passive transport is going to be diffusion. It's going to be down a gradient, so with the force that's pushing it. But that doesn't mean that it is always going to be able to go straight through the phospholipid bilayer. Sometimes we are going to need proteins, even though we're moving in a favorable direction. Okay. So one of those types of proteins we can think is a carrier protein. So this is a integral protein. It's a transmembrane protein, right? It's inserted in the phospholipid bilayer and it goes all the way across. And a carrier basically has a binding site that flips, right? So here we can see a glucose carrier protein. So here we have our ECF outside. We have our ICF inside. We have our plasma membrane, so our phospholipid bilayer, one phospholipid, two phospholipid. And we see our carrier going all the way across. So we can see that it begins with a binding site for glucose, touching the extracellular fluid. So if we have a glucose molecule, it can bind into that binding site. And then without energy, just like when our enzymes may change a little shape, when something binds to their active site, this carrier protein is going to change a little bit in shape just due to chemical properties. And it's going to flip that binding site to the inside and it'll move across. So even though we have a change in the shape of the protein, this actually did not require energy. This was just a natural reaction that that protein had to the glucose binding in. And that's why this is still passive transport. Diffusion, right? So we're still diffusing down glucose's gradient. So in this case, we would have high concentration of glucose here, We would have low concentration of glucose here. All right, so we're still moving in that favorable direction. The only difference is that glucose, not lipid soluble, it can't move through those layers of phospholipids. It has all those hydroxyl groups on it, making it slightly polar. It's carbohydrate. They don't diffuse well across lipids. So it has to go through this protein. But otherwise, the setup for the problem is the same. So when we think about rates of transport for facilitated diffusion, we're going to have to keep an extra thing in mind. So we're still going to see that as our concentration gradient, and when you see this delta symbol, this triangle, that's telling you it's a difference. So this is a difference in concentration. That's what that means. We can still see that as the concentration gradient goes up, that difference in concentration goes up. We see a greater net flux, so we see a greater movement. But because in facilitated diffusion, we have to use that transmembrane protein, we have to use that carrier protein, we're not going to see that direct one-to-one rise, because at a certain point, essentially those carriers are going to be full, right? So that's why we see this plateau, right? When we use up the available carrier proteins in the membrane, it kind of doesn't matter how much glucose is floating around outside the cell. If there's no protein that's available for it to go into, it can't get across. So you can think of them kind of like elevators, right? If they're full, you can't speed it up, even if there are a lot of people standing there waiting for the elevator. So that gets to the number of carriers in the membrane. And we saw this relationship with the concentration gradient that we saw in our simple diffusion as well. Now, a final factor that's going to affect the rate of transport is the rate of transport of the carrier itself. So basically how fast that protein works, right? That's also going to make a difference. So that's that first one. So in this example, we're going to talk about glucose transporter 4. So glucose transporter 4 is a protein. It's synthesized in the rough endoplasmic reticulum, so that one with ribosomes. Ribosomes can help us make proteins. Okay. These molecules get packaged into vesicles, so basically little bags of membrane, right? And what we need to know here, right, as we're thinking about physiology, okay, is that the presence of insulin is what tells your cell to take those GLUT4 transporters and put them into the membrane. So when insulin is present, this hormone, you're going to end up with more glucose transporter 4 proteins in the membrane. This means that you're going to be able to move glucose faster because we've increased the number of those carriers. One of the problems in diabetes can be that because we're not producing insulin, right, in diabetes, one of the things that can happen is that a lack of insulin produced by the pancreas when you eat means that there's no signal to the cell that it should be creating more of these GLUT4 transporters, that it should be putting them into the membrane. This means that glucose is kind of stuck at the same normal, like slow rate that it started with. So if you think about a cell like, draw a cell. Okay. So we're going to have like a before and an after cell. So the top one's going to be before the insulin, and the bottom one's going to be after. Okay. So like before we have insulin, the situation is going to be something like, we'll have, let's say we'll have a couple of transporters, right? So we can move some glucose. Let's say we're going to have like 3. These are going to be my transporters. Okay. We also are going to have little vesicles, right? That might be full of more glucose transporters, right? So they're basically hanging out here, ready to be inserted into the membrane, but we don't have a signal to do that yet. After we have insulin present, the cell says, oh, okay, we need to put more GLUT4 molecules into the membrane because insulin is telling me that there's glucose around. So we have our same original transporters, but now we're going to grab those transporters from the vesicle as well. Let's stop down here. All right. So this first cell could transport a little bit of glucose kind of slowly across the cell, but the second cell, after insulin has given us the signal to put more transporters in the membrane, can transport much faster because the cell has more locations where glucose can get in, right? So what we're saying is here about diabetes is that if our problem is a lack of insulin from the pancreas, we don't get the signal to put those membrane proteins into the membrane. So we're kind of stuck in the same situation. Glucose can't get into the cell all that much. So we have less glucose uptake. So it's called uptake when we pull these things into the cell, which means that the glucose is just going to stay hanging out in the blood, right? So it's going to stay where it was, which is in the blood, which means we're going to see high levels of blood sugar if we test. Because we haven't upped the rate of glucose, even though we have glucose uptake, even though we have glucose present. To recap, simple diffusion directly across that phospholipid bilayer. We had our facilitated diffusion going through carriers, which had those binding sites, basically pockets that flip sides. Now we're going to have diffusion through channels. So in a channel, still going to be a transmembrane protein, but it's just going to be open or closed. So we're not going to see a binding site in a channel protein. We're just going to have a doorway or a pore through the membrane. So this is just going to function like a passageway. Only specific things are going to be able to get through specific channels. So we'll specify that this is a sodium channel or that it's a potassium channel or so on and so forth. Often when we talk about channels, we are going to be talking about ions. That's just a kind of look forward. So the way this works, right, we have some subunits to this protein, it goes all the way through. This can allow specific things across. So when we're thinking channel proteins, we're still thinking just from an area, potentially with high concentration or along with the ECDF, right? So we're thinking still in that favorable direction, right? So from high to low, if we're thinking just about concentration, but since we know we may be thinking about ions, we may need to calculate our electrochemical driving force, right? So passive direction is just going to be that direction that we're being pushed. So this is also not going to require any energy. So types of channels that we'll see, aquaporins, and unless we tell you otherwise, just assume aquaporins are present in a cell and that water can get across. An aquaporin is a channel for water. Okay. So just assume that our cells are going to be permeable to water because of these aquaporins. But the ion channels, we're not going to assume they're there unless we talk about them. Okay. So the ion channels are going to allow ions to move across the membrane, specific ions. So a sodium channel allows sodium, a potassium channel allows potassium. Sometimes we're going to call them leak channels. So basically we're going to be able to leak a little bit of a gradient, right? Sometimes we're going to talk about gated channels. These are going to be channels that close in certain situations and open in other situations. That'll be important as we start to talk about neurons. And occasionally we'll see bidirectional channels where the ions can flow in two directions. So not all channels are necessarily going to be bidirectional, although honestly, I do think about all of them as kind of bidirectional. Okay. So factors that are going to affect the rate of transport here. It's going to be the transport rate of that channel. So you can think kind of like, how big is that passageway? Just like with our carrier proteins, the number of channels in the membrane is going to make a difference. you have a lot of channels, you basically have a lot of doors, we can have a lot of ions go through. And then the third piece, when we're thinking about these channels, we need to think about, are they open? Because sometimes we are going to see channels that exist, right? So we'll see channels that exist, but essentially they have a closed door holding them closed. And so in that case, they're not going to allow things to pass through. So their presence is not going to matter in that case if they're not open. And that'll probably start to crystallize in your mind as we talk about neurons in our next unit. So we're going to move straight into active transport. So passive transport, you know it's passive transport because we're moving in the direction we would expect if we look at the gradient or if we look at the electrochemical driving force, if we're talking about an ion. Active transport, we're going to be able to identify because we're going to be moving in the opposite direction. So if we ever see glucose moving towards an area where there's already a lot of glucose, we know that's got to be active transport. We see sodium moving to a place where there's already tons of sodium, we know that has to be active transport because we're going to need something to push us in a direction that the particle does not want to go. So this is not going to be spontaneous. And it's going to require some type of cellular energy, right? Often we're going to see that that energy is ATP, so we can use ATP directly. But sometimes we're going to kind of piggyback alongside the movement of another particle, usually sodium ions. And that movement of something else can kind of pull us through, kind of the way, you know, like if you're going through a rotating door into a hospital or something, if you're pushing that door, you can kind of pull someone else through, even if they weren't trying to go. Okay. So when we say the movement is uphill, what we're saying is if we're talking about a molecule like glucose, where we don't have to think about charges, we're moving from an area of low concentration to an area of high concentration. If we're thinking about an ion, we're thinking about moving in the opposite direction from the electrochemical driving force. So whenever you see this word pump, if something says it is a pump, that should immediately tell you that this is active transport. We're pumping, we're pushing, we're putting in energy in order to move these things. So when we say that something is a pump, we know that it is a membrane protein going to be involved in active transport. It's going to function as a transporter. So kind of like our carrier proteins in our facilitated diffusion, it's going to have binding sites. Also going to function as an enzyme. We say it functions as an enzyme. Its enzymatic action is that it's breaking down ATP, right? So the enzyme part is that it's catalyzing this reaction where we pull off a phosphate group and turn ATP, our adenosine triphosphate, into its lower energy form, adenosine diphosphate, just those two phosphate groups. So it's harnessing the energy in that final bond between those final two phosphate groups in order to power the movement of these particles across the membrane. So here we are looking at a sodium potassium pump. Just happens to be what we're looking at. So we can see these specific binding sites for sodium here. And we can see ATP getting used. And then later we're going to see potassium. And we'll see the role of that. And we'll go through the role of this pump, probably repeatedly. Now, these pumps do demonstrate saturation. And all that means is that those binding sites can be full, right? We have 3 sodiums in the 3 binding sites on this pump. We have a 4th sodium come along, there's no binding site for it, it's going to be saturated. So that 4th sodium wouldn't go anywhere in this case. So when we're thinking about active transport, we do divide in our heads primary active transport. So our first type of active transport from secondary active transport, our second type. And in a way, we can think about primary active transport as setting up the stage for secondary active transport. So let's talk about that primary active transport. So when we talk about primary active transport is going to be using energy from some compound. Almost always when we look at primary active transport, that compound is going to be ATP. All right. So primary active transport, we're directly using energy to push something across the membrane. So here we see that sodium potassium pump again. Okay, so here we see our ECF outside, our ICF inside. We can see sodium binding into those 3 binding sites. Then we break down ATP, and this causes a conformation change, so a shape change in this protein that pushes that sodium across. Okay, so when we had the carrier proteins with glucose, it just naturally changed shape, that protein. That's not what's happening here. Here we need the ATP in order to cause this change to push the sodium. So since we're looking at this sodium potassium pump, just to highlight this, right? We see sodium moving. So we could immediately know that our area of high sodium is going to be outside, and our area of low sodium is going to be inside, because we know that this is a sodium potassium pump, because we know it's using energy. That's got to be primary active transport. So we know we're going from low to high. We're going in an unfavorable direction. After we push the sodium out of the cell, we're not done yet. The other thing we have happen to go back to our original state is the potassium bit. So our potassium also has binding sites. So we have binding sites for 2 potassium. 1, 2. Potassium is going to bind in. This is going to flip and push the potassium into the cell. Okay. Our phosphate is dissociating here. This part is not terribly important, except for what we can realize is that as those potassiums get released into the ICF, we're going back to the original state of this pump, right? So there's a full cycle of a sodium potassium pump. We push 3 sodium in one direction. We pull 2 potassium in an opposite direction. So when we think about sodium potassium pump, these are both positively charged ions, but we're moving 3 sodium out, 2 potassium in here. So essentially, we're going to be changing the charge inside the cell because we are not equivalently trading sodium for potassium here. So we basically pushed sodium out of the cell, an extra charge versus what we took in. So the inside of the cell is going to become more negative in this case. So in secondary active transport, we set up a gradient, basically, by doing primary active transport. So say we use that sodium potassium pump. We pumped a bunch of sodium, right? A bunch of sodium out here into the extracellular fluid. And we have now set up a gradient of sodium. So in this case, the direction sodium wants to move is into the cell. So in secondary active transport, we would let sodium move into the cell. And if that's the only thing we had happening, right, we would call that passive transport. But what we can see here is that we're not just moving sodium, we're also moving glucose at the same time. So in secondary active transport, our sodium or some other particle moves down its gradient, moves in the favorable direction. And your cell is harnessing that energy with this membrane protein to move something else against its gradient. So if we were to look at this glucose, this red arrow in a diagram tells us this is active transport. But in this case, our glucose we'd have lots and lots of glucose already in the cell, right? So this would be our area of high concentration. Our glucose would have low concentration outside the cell, but we want to get all the glucose from our food, so we're pulling all that glucose through into the cell. So we're moving against the glucose concentration gradient into the cell by harnessing the energy from sodium flowing in the direction that it wants to go. So secondary active transport is named this because we set up a gradient with our ions, right, previously. So we had a pump happen that sets up a gradient, and then the second thing that can happen is we use that gradient to transport something in an unfavorable direction. We use it to do active transport of glucose here.
So if it was just a glucose, would that be primary then? And what makes the secondary is the addition of the sodium?
Yeah, if we just had the glucose here, yeah, we would need to directly use ATP or something, right? We need to get energy from somewhere, so that would be primary. Yeah, a hint for looking for secondary active transport that I do always look for is the number 2 secondary, right? You're going to always in secondary active transport see 2 things moving. That's absolutely true. Now here we're just summarizing what's happening in this sodium-linked glucose pump, we could call it, right? So it's a glucose pump, it's moving glucose. It's doing it through secondary active transport because it is letting sodium diffuse in the direction sodium wants to go, and that is actively helping us move that glucose. Now, another thing we might want to move, protons. So hydrogen ions, protons. So this is another thing that gets moved by secondary active transport sometimes in physiology. So we see the same sort of setup though. So we see sodium moving in the direction it wants to go. We can tell that because of this green arrow. But we see our hydrogen ions with their red arrow moving in a direction they don't want to go. So this is still secondary active transport. And the reason we're giving you this example in addition to the glucose example is to highlight that this ion that's pulling doesn't have to be going in the same direction, right? For like glucose and sodium, they were both going into the cell, and that was secondary active transport, but it's still secondary active transport if something's going into the cell and something else is going out of the cell. The key thing to look for is not the direction of those arrows, but whether we have something that's moving in the direction it wants to go and something else moving in the direction it doesn't want to go. So you may or may not have seen these words before at the bottom, right? So when we're moving together in the direction we want to go, I get back, okay. When we move in the same direction, we call it co-transport. So co-with is a type of co-transporter, moving sodium and glucose in the same direction. But we can also have counter-transport, or sometimes we call these anti-transporters, right? Antiporters. That just means they're moving in opposite directions from each other. But in both cases, they're examples of secondary active transport. So here is a big table of our different types of transport that we want to think about. So we can think about simple diffusion directly across those phospholipids. When we think about passive transport, we can think about going through a channel. We can think about facilitated diffusion through carriers. So you can see all of these are going down the electrochemical gradient. So they're going in a favorable direction, not requiring energy. But the difference is how they're going across, right? Simple diffusion, we aren't using a protein at all. Passive transport through a channel, we're going through an ion channel. Passive transport through facilitated diffusion, We're thinking like glucose getting moved by a carrier protein. And this has some of our other properties of these types of transport highlighted on there as well. Now, one of the reasons that we want to get set up understanding these different types of transport in isolation is because when we start thinking about physiology and we start thinking about systems in the body, a lot of things are happening at once, right? So we're going to see coordination, essentially, between active transport happening in some part of the cell and passive transport happening in other parts of the cell. Okay. So one of the reasons that intracellular fluid and extracellular fluid differ at all is because we have active transport, because we have pumps kind of maintaining gradients across. When we talk about maintaining gradients, we are often thinking about the sodium potassium pump. Okay. And creating that gradient is part of what's helping us create a separation of charges, which is part of what's going to set up electrochemical driving forces. And these gradients are often going to allow for passive transport elsewhere. So I'll trace out what's happening here. Okay, so here we see our type A primary active transport. Let's focus on the pump first. Okay, so sodium is moving from low to high. All right, so it's moving up its gradient. All right, up. Potassium, all right, is also moving from low to high along its electrochemical gradient. So it is also moving up. Happens to be in opposite directions. And it's primary active because of this use of ATP. Okay. And this means that we are maintaining these sodium and potassium gradients. So we're maintaining a low sodium concentration inside the cell because every time we have sodium come in, we push it back out. We're maintaining high potassium gradient inside the cell, right? Because we're pulling more and more potassium in, which means that if we were to look at ion channels elsewhere, like leak channels or something, we'd see that sodium is moving down from high to low, right? So ECF is still high. We still have low inside the cell. So this is moving down. So this would be passive. And that's through a channel. And the same thing is happening with the potassium at the bottom, right? So it's going from high to low, also moving down. So this is also passive. And this is also a channel. Questions about this kind of coordination? We're going to see in all sorts of places that especially setting up these sodium gradients is going to power a lot of different processes in the cell. That's why we spend so much time thinking about the sodium potassium pump. Go ahead and review with a question. So we're thinking about facilitated diffusion specifically. So remember what facilitated diffusion means. So hopefully for this one, we were all thinking about that example with our group 4 transporter, right? We're thinking about carrier proteins, right? So we're thinking facilitated diffusion. So that's passive. And diffusion in general is passive, right? That word. So facilitated diffusion is going to be passive. And we're thinking about carriers. Okay. So the speed with which that carrier flips across, the transport rate of that carrier, yes, matters. How many carriers we have in the membrane, yep, that matters. The magnitude of the electrochemical gradient, in the case of glucose, the chemical gradient, that's that separation, right? So when we're thinking which direction is favorable, which direction does that thing want to go, that's going to matter. Now, the solubility of that molecule doesn't matter. Does anybody remember when it was specifically that we needed to think about that solubility? It was a different type of passive transport. Yeah, perfect. Yeah, so the solubility of the molecules in the membrane only matters if they are soluble in that membrane. So that only happens with simple diffusion, where we're going directly across the membrane. We're going to think about another example that we could think of. So think about if you're in a situation, you're breathing, fluid starts to accumulate in the lung. Now, it is true that as you start to have fluid accumulating in the lung, this is going to decrease the ability of your body, of your lungs, to deliver oxygen into your blood. So I want you to think about why that could possibly be. While you're thinking about it, I would like you to think about how that oxygen would be getting from the lungs to the blood in the first place. So think about what type of transport that would be. So hopefully you started out maybe by thinking about oxygen and membranes, right? So oxygen is one of the things that can get across our phospholipid bilayer, right? So O2 can go directly across by simple diffusion. So that's passive transport, simple diffusion. Okay. So simple diffusion is where we're just moving directly across this membrane. It's not true that oxygen can't travel through water. It doesn't really care. It can move around that water. Water isn't changing the properties of the membrane or the oxygen here, right? It's not really reacting, not changing the solubility. But water is kind of acting like an increase in this membrane layer, in this thickness in the lung. And we'll see a specific disease state where this matters.